In these two examples, we are going to be trying to find the definite integrals, which means we would be finding the area under this curve. So these are a little bit trickier than in the past because we have a little bit more of a complex kind of a look to it. So things that we're looking for, is this a U substitution kind of a thing? To know that, I need to know if this piece specifically, I'm looking at this and saying, if I were to have done the derivative of any kind of an exponential, I would have done a chain rule to it. So if this would have originally had a chain rule to do the derivative, we need U substitution to undo the derivative. Same thing's going to go with this one, that you have an inside of a parenthesis kind of a piece. And so the derivative of an x squared, derivative of an inside, is going to give you an outside. So there's definitely a U substitution happening. So on an exponential, almost always your exponent is going to be your U. So I'm going to rewrite this as U equals x cubed plus 1. If I do the derivative of that, I get a 3x squared dx. So I have an x squared and a dx. So what I'm going to do is I'm going to rewrite this as a -1 to 2 e to the x cubed plus 1 x squared dx. All right. So that x squared dx, let's move the 3 over. So we'll divide that over. So a 1/3 du would equal x squared dx. All right. So now if I were to rewrite this, I would put this 1/3 in. And this is where whole goal of this U substitution is to make this a little simpler to undo. And so x to the third plus 1, we're going to rewrite it as e to the u. And then this x squared dx, we're replacing with the 1/3 and the du. So that's actually all we're doing the antiderivative of. So here's where you can code two different paths. So you could undo the antiderivative and then kind of like what we would have done in previous problems, you use your U substitution, you do your antiderivative, and then you pull your original values back in. And then we would be doing the fundamental theorem of calculus and plugging in our values and finding the area under the curve. Or you could, at this point, leave everything actually in terms of U, but when that happens, your bounds get adjusted. Because you're not going from a -1 to 2, you were on this equation, but you're doing different values because you've adjusted your equation. And here's how you tweak it. You just take these values and sub it in to this x cubed plus 1. So if I plug a 2 into this, I would have 2 cubed, which is 8 plus 1 is 9. And then if I take a -1 and cube it, -1 cubed is -1 plus 1 is 0. Those are my new bounds because everything is in terms of U. So I took these that were in terms of x's, plugged them in, and turned them into terms of U. All right, so now I can, and you don't have to do this. You can go back to the very beginning, but you're going to get the exact same answer no matter what. I just like to go ahead and sub it in and maybe kind of skip a step or save a step, I guess. So if I do the antiderivative of e to the u, that's going to be e to the u. And then we're going to have a 1/3 in front of that. And we're going to go from 0 to 9. And so we're going to have a 1/3 e to the 9th minus e to the 0. Right? I'm plugging in the upper bound minus the lower bound. And then that's going to give us basically an e to the 9th, but I'm going to distribute a 1/3 into that. So that's going to be a 1/3 e to the 9th minus e to the 0 is 1. So 1/3 distributed into that is just going to leave us with that value as the area under its curve. And if you did right here, sub back in your x cubed plus 1, if you plug that back in and you left your -1 to 2, you'd still get the exact same value out of that. All right, so just an option. So you'll pretty much see me do that every time. Okay, so on this one, most of the time when we have something in parentheses, that has a tendency to be our U value. So I have a U going to be equaling a 4 minus x squared. And the other piece we'll show you on this next step is if I am going to do the derivative of this, I'm going to get a -2x dx. And there is a 2x dx. So that is perfect, but I am going to bring the negative over. So du is 2x dx. So that's perfect because I can rearrange this with the negative 0 to 1, parenthesis, 4 minus x squared. And I can take that 2x dx, kind of put it onto the end. And it's perfect that I can sub that piece with a negative u. Oops, didn't sub it yet. So leave my negative. Right, so I'm going to now bring in the negative, but that 2x dx gets replaced with a negative u. The negative will be on the outside. This value is u. This value is negative du. I already have the negative. So that's it. That's all I'm going to look to undo. Now I need different bounds because I'm going to leave everything in terms of u. So if I plug a 0, well, let's plug the 1 in. So if I plug a 1 into this, I would have a 4 minus 1 squared, which is 4 minus 1, which is 3. And then if I plug the 0 in, I have 4 minus 0 squared, which is 4. So this would go from 4 to 3 of a much simpler type of a problem. Now, there is one little problem that we see, and this is going to happen from time to time, but there's an easy fix for it, is that that's not in the correct order. I always want to go from a small to a big. And there's nothing I can do about it. That just happened when I plugged those values into it. I didn't do anything wrong. So remember that you can switch this. My original has the negative. When you switch the order to this, we negate it. So we multiply it by a negative. Well, then that negative is just going to undo the other negative. And so now we do one little switch, apply a negative onto it. Now we're ready to go. So that's going to cancel away. The antiderivative of u, we're going to add a power, divide by that power. So we're going to have u to the second over 2 from 3 to 4. And now we'll plug in our stuff. Let's get our final answer here. So we're going to have a 4 squared over 2 minus a 3 squared over 2, which is going to get us 16, so 8 minus, we have a 9 halves, so minus 4.5 is going to get us an answer of 3 or 3.5 or 7 halves. All right, so those were a couple examples of manipulating it into u, changing your bounds based on these equations, creating new bounds, keeping everything in u, and then going ahead and finding the area under that curve.